when you had exponential growth and decay, they both use the same generic formula. Y equals A times B to the X minus H plus K. And that's what it looked like as a shifted function as far as growth or decay was concerned. The differences in live, or sorry. Excuse me. The differences between the two were dependent upon the value of B. Okay. So what happens is the value of what happens here is that the value of B is what distinguishes between which one you're looking for. If B is greater than 1, it's growth. If B is smaller than 1 but bigger than 0, it's decay. Now, after that, one of the things that we looked at, yes ma'am?
What if it is 1?
Then you have a constant function.
Okay. It's like how would you write that? Like,
It won't be growth. B's never 1. It won't be a growth function. It won't be growth. Because what's 1 to any power? 1. It's just linear. It's just a linear constant function. It has. That's why it's the differences between the two. Okay. Now, when you had growth and decay, you had two different types of graphs. And this kind of helped us to figure out what they were going to look like later on when we talked about graphing with E. The graphs for growth or decay are dependent upon A value. They look similar. The directions are just reflected over the y-axis. So if A is positive, your growth does that. And if it's negative, you reflect it. It dives away. The reason why I wanted you guys to know that was because when we graphed the exponential functions, when you're not using a calculator, you can't calculate values in E in your head. You can't say, hey, it's 2.71 whatever to the third power, and you try to figure all that out. It's just plain old stupid. But if you know how to find y-intercepts and asymptotes, you can shift and move those, and you know the general idea of the curves are going to go, because it still mirrors the same idea as growth or decay, but it's just ever so slightly different because you look at R instead. So growth can go up and right, go up to the right, or dive down from the right. Decay, if A is positive for decay, it's doing this. If A is negative, it's doing that. Now, when you looked at the exponential one, really all you had to worry about was, not X, excuse me, it's R. It was RX, right? Yeah. And it was, I think we had attacking X minus H. I don't think we even had a shift in here, to be honest with you. I don't remember. The R value is what told you if it was growth or decay. If R was positive, growth, R negative, decay. And really all you had to worry about at that point was asymptotes and intercept. And it was very, very quick. And we saw that yesterday. It was really quick. I don't think you guys have an issue with that at all.
And then what does it look like?
Yeah, and then you just, and that's the idea. If it's growth, then it just comes back to here.
Oh, okay.
And if it's decay, it comes back here. And you just go back to the same rules of A. It follows the same patterns. Yes, ma'am?
do you want us to know like which ways the graph will go for growth and decay?
Well, you should, it's nice to know that, because if you're graphing this without a calculator, you should know which direction it should be going. So when you start substituting in values that are easy to work with for growth or decay that would work, you know if you're in the right ballpark. Same deal with exponential. If you're graphing that, it's a pain in the butt because you can't do decimals in your head. But if you know where your intercept is and where your asymptote's going, you're gonna know which way it's moving up and away or coming down because it follows one of those 4 rules. And that's the idea. As long as we can get the idea of a visual of what it should look like, we're gonna be okay. And then later on, we talk about logarithms and natural logs, and we look at those graphs, same deal. They're gonna be tough to work with, but if we know the general consensus of directionality, we're gonna be okay. So let's look at an example then. Accidentally close these out. Oh, this is and I want to go through this and just do a quick rough sketch via parent function and shift. And I want to list out my ordered pairs. Just kind of go through the whole list here real quick and see how it goes. So we have y equals 2 times the quantity, 2 to the x minus 1, all plus 4. Which means that I have a parent function at 2 to the x. We okay with that? That means I have an a value of 2, a b value of 2, and I just go from there. Just like always, for growth or decay. We're going to pick very simple numbers and plot through it. By picking simple numbers, we're going to see what's happening on both sides of the excuse me, of the vertical axis. We be able to see what's happening on both sides, so you know which way it's diving and going through, in case you forgot your rules of A. It helps. So, when you have 2 to the negative 2, what does that become? 1/4. So what's 2 over 4? Half. So at negative 2, you're at a half. 2 to the negative 1 is? 2 over 2 is? What's anything to the 0? 1 times 2. 2 times 2. And then 2 times 4. 8. Quick ordered pairs. Nothing that should be horribly scary to work with, even fractionally. If you go back and think about the stuff that we did before with fractions, the fraction ones that we had, they weren't terrible to work with. You always wanted to be able to simplify something through. It wasn't anything that you had to worry about. So when you go to look at the graph then, we know to start this one, we're going to have, wrong button. We'll have our asymptote for the parent at 0. I know that I have a y-intercept at, excuse me, at 2. And then I just go through. So half, 1, this is 4, and 8. Now, we've done this next step before a little bit differently. Before we've done this, we just kind of moved it and went on. I'm going to show you how you can do this with the ordered paired values first. Some people find it to be a lot easier to do it that way instead of trying to count on a graph, because sometimes you get lost on it, but knowing what your shift is, it's pretty easy to go through this. If I go back and look at my shift, it was it right or left 1? Right. It's right 1, and then what was it, 4, I think?
Yeah.
Is it up or down 4? Up 4. So that means that to all of my ordered pairs here, the x coordinates, I have to add 1. So here, I'm going to take my y values and add 4. So I get negative 1, 0, 1, 2, and 3, 4.5, 5, 6, 8, and 12. And I've just listed my next 7 ordered pairs. A lot of people find that to be much easier to list the ordered pairs before you do anything else. There's a reason why I like to show you guys that step, and it's going to come in later on when you see this. when you go through stuff like that via trigonometry, there's a big reason why it's so important to be able to understand how ordered pair shifting works, because adding and subtracting in pi over 4 is going to be a lot easier on paper as a one-step equation almost, as opposed to trying to count it later on. Okay? So doing this, we get new ordered pairs. -1, excuse me, 4.5. 0 and 5. 1 and 6. 2, 8, and then up here. My new asymptote goes at 4.
Why do they cross each other?
That's fine. Does it really technically cross it?
Well, it kind of just, it goes through. Because like they have the same, they have one of the same points.
And that's okay. Because this is just to help you get the general consensus of where it's going. And this is where it really is. All right. Shifting via parent. When you start to plot your parent function, it's to get you in the general spot, and then your shift works. And really the whole big idea of being able to do this is so you can do this. Okay? Because if you, they're kind of, this is kind of important to be able to do for later on. So we start small with easy stuff. Trig is so awesome, it's so much fun. Trust me, it is. You might have a little fun. Okay? And that's how that would work. Now, the difference between this and a decay problem is just that your decay ones have a fractional b value. Here's one I did earlier. This one. Now, when I look at this one, it has to be decay because your b value is less than 1 but greater than 0. Excuse me. I still have an h and a k. I'm still going to plot via simple sets of ordered pairs. The reason why I'm going to use simple sets of ordered pairs for these things is because of the fact that it's a growth or a decay problem. I'm going to use all 5 ordered pairs. If it was just an E problem, I'm going to plot one thing and an asymptote. And I should have enough time to get through an example of that as well. Here, what's your parent function? And there's your parent function. Again, you're just picking -2, -1, 0, 1, and 2. Those are the easiest ones to work with. It looks like it's going to be awful because you've got fractions, but when you start putting it together, it's really not that bad. Because if I take a fraction to a negative exponent, what do I do to the fraction? Flip it. So what's 3/2 squared? 9/4. What's 9 times -3? There's your first fraction. 2/3 flipped. 3/2. -3 times 3. Anything to the 0? 1, so this gets -3. And then I have -3 times 2/3. And then if I square 2/3, I get 4/9. Which becomes what? -4/3, very good. So it's not that the fractions here are awful. It's just remembering your properties of exponents. Now, to each of those ordered pairs being the parent function, what would I have to do to them? Here I would have to do what? Subtract 1. And then here I would have to do what? Add 2. Now, for the lack of time here, I'm just going to go ahead and show the ordered pairs. Well, I'll just do the fraction ones because I think you can do these. Okay. Now, when I'm adding 2 to negative 27 over 4, would I just add 8 over 4? So what's negative 27 and 8? Did I say negative 8?
Where's it 8?
Oh, okay. And then what's negative 4? I'm sorry, what's negative 9 and 5? I'm sorry, I got ahead of myself. I was giving the answer. It's be negative 5. It's be negative 9 plus 4 halves, so you get negative 5 halves. Negative 3 plus 2. And then negative 4 thirds, I'm going to add 6 thirds, and I get 2 thirds. So in essence, even though there are fractional amounts that you're putting together, the way that you're getting and using quick common denominators isn't going to be awful. They never really are. I try to make sure that anytime you have fractional b values, they're thirds and halves. I try not even to use fourths because those can get kind of messy after a while because you have to square it and flip them and all that. I think thirds and halves are pretty decent because I don't want you to use calculators. I don't think you need it. Okay? Is that fair enough? Now, I'm going to skip ahead and go to the asymptote. Where's your original asymptote?
0,
Where's your new one?
2.
Okay. Now, if I go to an E problem, I just have a bunch of review stuff. I just put together a bunch of worksheet stuff that I have. If I go to an E problem, you have your E stuff is y equals a times e to the r rx is your generic. It is growth if r is positive. It is decay if r is negative. And then whether or not it dives up or dives down then depends upon a. That's why I want you to revert back to the rules for growth and decay via a. So here, whenever you have an E graph, all you have to find is the parent function's y-intercept and the parent function's horizontal asymptote. Well, it's nice because the horizontal asymptote is still going to be at 0 because it's growth and decay. So let's figure out our parent function here is going to be y equals 2 e. What's my rate? 1. Good. It's going to be 1 because there's nothing in front of the x. So now this means that on a short graph of what you did last night, where is your y-intercept to start? 2. Because if x is 0, what's anything to the 0 power? What's 1 times 2? 2.
So will it always be the leading one?
Yeah. The parent function, your y-intercept is always a, whether it's growth, decay, or e. Parent functions always have the intercept at a. My asymptote to start is going to be at 0, just because it's e. But then, now with the e problems, you always go back then automatically to your shift. This case here, I have a negative 4, I have a x minus 4, and then I have a plus 1. Which means what direction is it going, left or right? Right, how many? 4, and how many up or down? Up 1. So basically what I have to do to this then is just count over 1, 2, 3, 4, and up 1. And I have to figure out what that ordered pair is. Well, 1, 2, 3, 4, 3. And where's my new asymptote? Yeah, it's at 1. Now, we have to think about what the curve did. Was this a growth or a decay problem? Its growth. Is the A value positive or negative? So this is an A positive growth, so it's doing that. So my non-shifted and my regular. That's all you can do with E graphs because you don't have a calculator to plot any other points. When we get to logarithms and we graph logarithms next week, all you're going to be able to find out is 2 points. Yeah?
Is that a new chapter or is that within chapter 8?
It's still within the chapter.
So this will be on our quiz?
Yeah. Yeah, what happens, logarithms are just funky exponents. Logarithms allow you to do this. What's 2 squared? What's 2 cubed?
8.
8. Then what's 2 to what power is 6? That's what logarithms let you do. Yeah.
Can you help me with the decay with the fraction?
No. Are we okay on this one?
Sure.
We got half more.
So we're not doing like first and lateral?
Yeah, it's all in there. It's all in 8.3. So then the other part on here were your formulas. You had standard growth, just a regular growth rate, was y equals, what was it, your initial amount, 1 plus your rate to the time. Then the decay was your initial amount, 1 minus the rate to the time. And then you had interest. If it's compounding interest, principal, 1 plus the rate over n to the n times t is your total, or your amount, I guess. I didn't use a here, did I? Did I use a or was it p? I thought it was, I'm sorry. Yeah, is your initial amount, yeah. And then if it was a continuous compound, is per. And remember, n stands for the number of times something compounds.
Are we gonna get these formulas on the test tomorrow?
No. Yeah, no. Yeah, Fleming.
Are you just gonna have like word problems that you want us to use this week?
It'll look like what we've done. Why change it? All right, why change it? Is that what you're looking at?
Oh, I'm just having trouble
Get a common denominator. If you're adding 2 to something with 4, that's 8 over 4.
Oh, okay.
Does that make sense? You always use it as a common denominator in work through it. What I got here is I just ran off a few of the old worksheet stuff. I would just kind of putz through these things and see if you know how to do some graphs, see if you can answer the word problems and go from there. Or you had to find the slant.
I didn't do it.
How do we do the E stuff?
This year was like how many times a year?
We just did that. We literally just did that. On how to do that.
Is there, if it says it's compounding quarterly, semi-annually, daily,
I'm pretty sure
it's the number of times it's compounding. If it says it's compounding continuously, it's per. That's it.
Like just today. What's fun just today?
It's all today for quiz.
Yeah, before the quiz. Like this stuff.
Okay, let's just make it clear. How do you get it fresh?
I thought it was gonna be on Thursday.
Really?
Yeah, I've never heard you say her name before.
Sorry.
No.
Sorry. So, I'm sorry. All I'm looking at here is I just threw a bunch of stuff at you guys so you can try stuff and look at them, okay? There's just a whole bunch of different things on here, a bunch of, substituting in, find values, things like that. I put some depreciation things in here, depreciation stuff. I don't have the answers. Alright, so if I put -2 into the parent. that means it's 2/3 to the negative, which means I flip it to square. So if I flip 2/3, I get 3/2. What's 3/2 squared? What's 3 squared? Yeah.
What the heck do I do? I'm not even going to go. I'm going to
Yeah, I honestly don't know if I have.
Nice fish restaurant. No, this is my only class class, dude. I got 87.